Thanks y'all for coming. This is one of my favorite conferences. I'm so happy to be here. So my name is Josh Wills. I used to be Cloudera's director of data science. Left Cloudera a couple of years ago to become Slack's first director of data engineering. But recently I left management. I left management about 2 months ago, and I am now just a software engineer. And it is amazing. Thank you. For those of you who are giving thought or have considered going into management, I have a little bit of advice. This honestly could be like a whole other talk I could give about leaving management. But the reason I went into management was that I like to solve people problems with technology. But that's not actually what you do in management. In management, you solve technology problems with people. Not actually as much fun. So as I kind of made my way up the management hierarchy, there's a sort of a joke about law school where it's a pie eating contest where first prize is more pie. That was what it felt like. The higher you went management, you looked up and it was like, wow, it's just a lot more pie up there. So anyway, so now I just do real stuff. So I work on Slack search engine, search indexing pipelines. I'm doing some machine learning stuff that I will not talk about right now because I've only been doing it for like 6 weeks. But I thought I'd talk about some other stuff instead that I thought was interesting. I want to talk about the intersection of technology, product decisions, and policy as it relates to machine learning, or at least as it relates to how we do machine learning in 2017. And this is all a bit strange for me because I've been doing this stuff for about 10 years now, and my last decade looked a lot like this. It was pretty much all technology all the time with like a very small amount of product and a very small amount of policy related stuff. But mostly when I talked and when I spoke, when I read, all the things I did, it was really about data and technology. So for perspective, I used to work at Google. I worked for Google from like 2007 to 2011. And then after that, through a series of unfortunate errors, I became a manager and a director. So I haven't really done like real honest-to-God work in about 6 or 7 years, broadly speaking. So when I'm describing this, I'm talking about what it was like to do machine learning at Google in 2011, which, to translate to the real world, that's like what it was like to do machine learning in 2015, roughly speaking. I felt like that would have been funnier. Okay, no? All right, not really. All right, it's fine. I worked on ad click prediction, like so many of us have. And when I was doing this stuff, first and foremost, the product problem was kind of a given. Like you were working on fraud detection, or you were working on spam, or click prediction, things like that. It wasn't really it wasn't hard to figure out what the product was supposed to do. It was supposed to do that. It was supposed to predict the click, predict the spam. That was the job. It was very simple. It was very clear. Along with that, there wasn't really much in the way of like policy concerns, or you weren't like super worried about like what is the government going to do, or like, it was either like very well defined for stuff like fraud, like there were very clear guidelines, or you were doing ad stuff, which was essentially like lawlessness, and you do more or less anything you wanted. So it wasn't like policy wasn't something you had to worry about really. And so therefore, everything was about data and technology. And all we did was we like picked a pretty simple algorithm, like usually logistic regression, and then we engaged in like years and years of feature engineering and experimentation over and over again. And that was like basically what we did, and it was kind of great. So that was like my perspective on what machine learning was like, circa 2011 at Google, broadly speaking. So here's me. I'm an engineer again, and I'm back hanging out with my other fellow engineers, knowing things that are like 6 years old, roughly speaking. And so like being back doing real world, honest to God machine learning now, I just want to kind of give you guys a context of like how old and ignorant I am. I didn't know what XGBoost was. I was expecting like sort of shocked horror from the audience. No, okay. Does anyone here not know what XGBoost is? It's too late to admit to it now. It's shameful. I've ruined it for everybody. XGBoost is great. XGBoost is amazing. Like algorithms have gotten way better. Like this is really good news. It was very exciting for me to come along. So like really fairly basic stuff I kind of had to like get up to speed on again over the last couple of months. There's other stuff that was like much more shocking to me. In particular, embeddings. Oh my God, embeddings are amazing. Have you guys ever done Word to Vec? It's super, super cool. Did anyone? Okay, everyone knew this already. That's fine. Yeah, I am sort of shocked at how quickly we dive into doing machine learning problems now. Like how quickly we dive into feature engineering. Like things we used to spend all kinds of time agonizing over and like manually coding features and all this kind of stuff. We just don't do that anymore. It's a waste of time. Let the computer do all that work. It'd be like, trying to describe it's like discovering garbage collection or something like that. I don't have to manage memory anymore. This is amazing. Why aren't people more excited about this? Okay, anyway, it's like I'm traveling like back from the past and I'm describing what the present looks like. It's not super helpful. Yeah, like this is just really, really exciting to me. It just sort of blows my mind. Back when I worked at Cloudera, I had this nerdy abiding passion for seismic data imaging. Seismic data imaging is this process by which oil companies go out and they collect all of this data about what the subsurface Earth looks like, and they analyze it over months and years, and they try to use this data to figure out where to dig for oil, like where the oil is underneath the ground. It's very, very cool and very, very expensive, and they spend all kinds of money and all kinds of time analyzing this stuff. And I go start looking up, okay, like what's the state of the art in this practice now? And the state of the art now is you just take the raw data from the seismic processing and you use the historical models of where the oil actually ended up, and you do an entire process that used to take years in a week. I'm like, oh my God, this is amazing. This is absolutely incredible. All right, I'll promise I'll calm down about this stuff at some point. But yeah, this is just stuff that's blowing my mind. It's a very, very exciting time to be alive. It's also kind of a horrifying time to be alive, and we'll talk about that a bit more. So now, like everybody else, I've spent a lot of time on archive sanity, just trying to keep up with what the hell is going on, right? As sort of the pace of things go on, because that's my experience of machine learning now. Things that used to take months take days. Things that used to be impossible take months. And it's just kind of blows my mind that it's changed everything about how we work. This sort of time it takes to build and train models has just collapsed completely. And so this backlog of problems that we had never applied machine learning to before, we're applying it continuously, constantly, and the flood of papers and research and advances that are coming is just absolutely unbelievable, unsustainable. So yeah, that's all super, super exciting. At the same time, I think we can go further, and I think we have to go further, and I hope we do go further. Right now, the amount of work that goes into building the deep architectures that apply to a particular problem, it kind of reminds me of what computer architecture was like in the 70s. If you've ever read, the soul of a new machine, that kind of thing. We're talking about different companies building their own custom architectures because performance problems weren't good enough, so we're using custom CPUs and custom circuit boards and custom programming languages and all this kind of stuff. That is sort of what it feels like to me around deep learning right now. We're trying to apply deep learning, deep models to all these different classes of problems, and we keep building sort of custom combinations of layers that are all secret and proprietary and stuff like that in order to optimize a particular problem. And that's totally fine. That's again, infinitely better than what we used to be able to do. But the thing I'm really, really excited for is stuff I'm really excited to be able to move my slides forward. And then once I do that, auto ML. Google's been Quoque Lee usually speaks at this conference, and I don't know if he's here this year, but this is Google's attempt to build machine learning models that build deep learning architectures for us. And they started out doing it on a very, very small set of, relatively small problems, but recently they've managed to scale it up to significantly large problems. And this is very, very exciting. This is someone inventing the C compiler or something like that, building a cross-platform, cross-problem way to build up deep learning architectures to apply to any problem. And there's been some sort of articles about this, about how it's going to put deep learning people out of business, and I'm that's great. It's about time. But it's the same kind of thing. It's the C compiler didn't put assembly programmers out of business. There are still problems that merit having custom assembly code written. But for everybody else in the world, opening this stuff up to a vastly broader audience is nothing but good news, broadly speaking. So I'm just so excited about where the trend is going here in terms of what we're going to be able to do, what becomes what used to be as impossible becomes cheap, becomes like not that big of a deal. And so as a result, we spend most of our time talking about technology. There was a great tweet the other day. Someone said, most people keep talking about what we can do for generalized adversarial networks, but to what we can do for GANs, but not talking about what GANs can do for us. And that still basically feels true to me to a certain extent. We keep thinking about how do we tune these things, how do we make them better, how do we improve the technology, and not enough time thinking about how can we use all of this amazing, amazing technology we've built to make human problems better. And there's some reasons for that. And that's, at least I think there are some reasons for that. I want to talk about what I think those reasons are over the next few slides here. I'm going to eventually learn how to click the slides forward, I promise. All right, so let's talk about the data product problem. The reason the data, so back when we were doing like fraud prediction, spam prediction, ad click prediction, the reason the product problem was very tractable and very easy was that the problem was clearly important to the companies that had it. And so they went out of their way to collect detailed, high quality data about that problem in order to make it amenable to the kinds of analysis and the kinds of machine learning that we were doing like 5 or 6 years ago. Nowadays, though, because the cost of doing the sort of actual machine learning model creation and optimization has shrunk so dramatically, we now have the potential to apply these techniques to problems where we never really thought they were important enough to merit careful collection of data and sort of high quality data curation and things like that. And the only reason we've been able to make these advances is because people like the folks at Princeton who built ImageNet back in 2009 had the foresight and the genius to like realize that this stuff was going to be useful. Does anyone, like, you guys ever read the story of how ImageNet was created? Like, they couldn't get funding for the project for years. It's like literally like one of the most fundamental contributions to humanity ever was the building of ImageNet, and like they couldn't convince anyone to let them do it back in like 2008. It was a function of like a lot of vision by Professor Lee at Princeton. It was a lot of like, it was Amazon Mechanical Turk. It was like making this stuff possible. But broadly speaking, this is the problem we have today. If the data for a problem exists purely in a digital form, even if it's imperfect, even if it's dirty, like whatever, we can probably solve it, or at least find out relatively quickly if we can't solve it. Like, we can find out in a matter of weeks or months whether it is possible for us to make improvements or predictions from this model. It's not years, it's not an indefinite amount of time, it's like a finite amount of time you can make these decisions. And so the problem is now entirely, does the data exist in one place in a completely digital form? When people like talk about what jobs are we going to lose to machine learning, you basically look for the jobs where all of the data that people work with is available digitally already. I hypothesize that the very last profession to be killed, sadly, unsadly, politicians, probably, right? Because they have no incentive to make the data that they, you know, the backroom deals and stuff digital ever, and they, anyway, that kind of thing. Maybe we'll find a different way, who knows? All right. Broadly speaking, the whole product problem now is how do I build one of these data sets? How do I get all this data together? The common approach that you see among a lot of startups right now is basically similar to how we handle like marketplace problems. It's a chicken and the egg situation. I need buyers and I need sellers. So I need to find a way to solve this chicken and the egg problem, which Google has done and Facebook has done, Uber has done, Airbnb has done. It's a solvable problem. And the way this typically works is people come up with like a fairly clever way to acquire this data. A couple of my friends work at a company called Rumbix. They're trying to apply machine learning to the construction industry. And so they've built all of these really cool tools that help them capture all this data about how people build buildings and all this kind of stuff. And it's like a good way in for them to get a training set together while still providing some useful value to companies that are using their products as they go along. I saw this great article the other day where if there's some service where if you get hit up by a Nigerian, like, you know, 419 scammer, like someone who wants to trick you into giving them money, like that kind of thing, you can actually forward their emails to this company, and the company will kick off a chat with them in order to gather training data from them, basically. Like they'll essentially like engage and like try to trick the spammer just so they can get their data. Like brilliant. I mean, this is like really, really good stuff. This is kind of the sort of like innovative product stuff we're talking about. This is how people are tackling these kinds of things. And this is, a super valid approach. This will probably work in a lot of cases. My concern, though, is once it does work, or where it does work, I worry about, and I know I'm not alone in this, but I worry about the black boxes we're building. I'm worried about building like systems and processes that no one really understands in order to solve these problems. Like the seismic data example I'm talking about had months and months and months of work from different experts across all kinds of different fields, getting collapsed into a few days, of work by a bunch of computers to build a model that largely accurately predicts where oil is, but one that no one actually understands. And so there's not a way to figure out like how did this thing ever work. And there's research to solve this problem. We are working on interpretability, working on models like the sort of the teacher-student model where a simple model tries to figure out how a complex model works, like all that kind of good stuff. And it's required and it's necessary, but it also gives me pause. I have a kind of a weird book I like. It's called I Wear the Black Hat. And it's by an author named Chuck Klosterman, who's an essayist. And it's a book about villains. And the central thesis of the book is that in any story, the villain is the person who knows the most and cares the least. So for example, in Frankenstein, the Frankenstein monster isn't the villain. The Frankenstein monster is the monster. The villain is Dr. Frankenstein. He knows how to build, well, I guess he knows how to bring people back from the dead or whatever. And he doesn't care how anyone else feels about that. And so he goes ahead and builds the monster anyway. And it's not to say, like, I don't want to, like, we're not bad people. Just because you're a bad guy doesn't mean you're a bad guy. But we are the people who know the most. And so the standard for what things get done is basically who among us cares the least, roughly speaking. And that's kind of sad. And I'm sorry to be like super depressive by saying that. But I think it's essentially true. We are the people who know the most and care the least. And that's like a fairly heavy burden. I worry all the time about building things and not having the foresight, because I'm just as flawed and imperfect as everybody else, to know the consequences of what I'm doing, and hurting people who can't bear the cost nearly as well as I do. And so I'm wondering, like, what do we do about this? What can we do about this? What is possible to us? It's a really good article. Yeah, I know, I try. It's a really good article. It's been floating around the past couple of days. Something is wrong on the internet. And if you haven't read it, I highly, highly recommend it. It's basically about all these crazy, like, creepy as fuck videos on YouTube that are targeted at, like, little kids, and are just purely computer generated at this point, just to mint, like, ad dollars and stuff like that. Yeah, there's like some really, like, deeply, deeply disturbing stuff out there that is targeted at people who are vulnerable and who have, like, no power or no ability to, like, fight back at all against what is being done to them. These things have consequences. These collective action sort of problems have consequences. The other, our thing this week is Facebook developing systems to fight against revenge porn, where you send some nude pictures to Facebook and they will have someone look at them and then train models that automatically detect if someone uploads your photos. And this is kind of weird, and it's funny, and it's sad, and it's all these things. But it's also it's funny because, like, does anyone really trust Facebook with this data? Does anyone really? And why don't we trust Facebook with this data? Why don't I trust Facebook? I don't. Why don't I? I mean, I literally don't know. I'm, like, asking. If someone knows, like, tell me during the Q&A section. This is a useful thing. This would be, like, a good thing to have. This is a real problem that hurts a lot of people. It would be good if someone had a data set large enough to be able to, like, detect when this happened and prevent it from happening. But we don't trust the person, the entity, the thing that is in the best possible position to do that work with the data required to actually solve it. The technology exists clearly. We can do this. If we have the data and the training data to do it, it could be done, but no one wants to incur the costs because we don't trust the person who could do the work. That's the consequence of being a villain. That's the downside of it. It doesn't just hurt Facebook or Google or whoever, it hurts everybody. We're all worse off as a result of this. So we're in sort of a weird collective action problem situation where the data to solve a lot of problems does exist. It's just distributed all over the place. No one has all of this data together. And as a result, it's really, really hard to come up with a way to trust at scale that whoever collects this data will do nothing but good things with it because they're the person who knows the most and cares the least. And so this, to me, this is the problem to solve. How do we do this? There are a lot of computer scientists and economists and very smart people, friends of mine, people in this room, who work on collective action problems for auctions, for fairly allocating like the rewards from machine learning competitions, like ensembles of models, all that kind of good stuff. And this right now, this is the problem we need to solve. I have thoughts on how we might do it from a human perspective. I don't know all of the like algorithmic fair allocation stuff here. But one of the ways I think we can start on this is by starting very, very small. Like it's hard to trust at scale. It's much easier to trust with a relatively small number of people. And one of the things oil companies do when they're collecting all this seismic data for processing is they share the costs of sending boats out into the Gulf of Mexico to like locate where the oil is and gather all the data. Because there isn't a competitive advantage for them in having different data than other people. It's totally fine to have the same data as everyone else. The competitive advantage is in the analysis. And so it would be possible for them to like gather this data together and build giant shared machine learning models that would make all of their work vastly much more efficient if they're willing, of course, which is a big if, to trade off some of the advantages that accrue to having the differentiated analysis and so on and so forth. I think honestly, going forward, where differentiation will occur is in the ability to analyze the black box and not building the black box itself, if that makes sense. Like understanding how the black box works will be what differentiates, not the off-the-shelf AutoML C compiler thing that builds the model for you. That's my thinking. But start small. Start with institutions that already exist for allowing different groups of people to collaborate with each other when the stakes are relatively low. And we can start figuring out, like roughly speaking, how this stuff is supposed to work. And from there, we can scale things up a bit. I think information security, I think network security is an area where if we could get all of the companies together, if we could get everyone's data together and figure out a collective action system for allocating credit and rewards and value across all these different contributions, we could do a vastly better job at protecting against network intrusions, hacking, all this kind of stuff. It's just a really, really, really big and hard collective action problem. But again, there is a sort of back channel set of info security people that exist across all these different companies that if they wanted to do it and had a fair mechanism for making it possible, I believe it could be done. And I believe these things are prerequisites, necessary prerequisites on the path to the largest scale and scariest versions of this collective action problem, where we start aggregating people's health information together in order to like be able to predict diseases and stuff like that. I don't think there's ever a way where we're going to trust any single entity with all this information. I think we need to find a way to separate out, create clear sort of checks and balances between the people who know the most and the people who care the most in order to enable making this sort of stuff possible. And yeah, that's my presentation. Thank you all very, very much.